Hi, welcome to another video. So in this video, we're going to start talking about rational functions, and they're exciting. They're fractions, but they're kind of exciting because we get some very cool pictures out of them. We can graph them, and I'm going to teach you some great techniques on how to graph rational functions as easily as I can make it for you. And how we start with that is understanding really what a rational function is, that they are fractions, and fractions can cause some domain problems when we're talking about functions that polynomials couldn't. So here's what rational functions really are. Rational functions are fraction functions where we have variables on both the numerator and the denominator. The denominator is required to have variables on it, otherwise you really get a polynomial because you could just divide every term on the numerator by a constant on the denominator and create this polynomial that had fractions as coefficients. That's not really what we're talking about. We're talking about a polynomial divided by a polynomial that has variables on both the numerator and denominator. Those can cause some really interesting things to happen. So when we're talking about these fraction functions, we really need to understand that because we do have variables on the denominator, we can get some domain issues. Now, you should remember about domain. Like when we talked about fractions, you go, oh yeah, the denominator can't equal 0. And if it does equal 0 on the denominator or bottom of a fraction, we get some problems. What we're going to do is start defining those problems as graph issues. You see, we get two types of graph issues. So what you're going to learn in this video is that when your denominator equals 0, we are either going to get a hole in our function. Graph goes along, misses a point, exactly 1 point, and continues. It actually kind of meets that hole. We'll use that. We will absolutely use that when we're graphing. Or we get what's called a vertical asymptote. It's like a force field. It's like this graph goes along and goes, oh no, and then, or oh, and it can't touch it. There's no way for this graph to interact with that vertical asymptote. Well, I won't say interact, touch this vertical asymptote. And so we get one of those two ideas. So our job is really to discuss when you get a hole and when you get a vertical asymptote. The hole only looks one way. There's a hole, you just kind of miss a point. Don't miss the point. And then vertical asymptote, what those things are, vertical asymptotes is plural. A vertical asymptote individual is one, and you might have several, so that's what we say can be several vertical asymptotes. It's not called a vertical asymptotes. Don't do that. I've heard lots of students say that, but asymptote, like that, is an individual. So we're going to talk about the four ways you can see those. I'm not going to give you anything definitive on, oh, you're always going to get this or this or this, which happens to be my 4 favorite dance moves. But we will talk about that you will get those, and I'll show you later when we get to sketching and graphing rational functions when those happen. So let's get right into it. So if fractions cause domain problems, and if the denominator of a rational function equals 0, and we know that we get those domain problems, what those really are called is a discontinuity. It's where your graph goes along and then you miss a point, or you get this place where you can't continue, like a force field, like a vertical asymptote. Those things don't happen in polynomials. Polynomials are smooth, fully continuous curves for the entire domain, which is all real numbers. So they go forever and ever, creating these really smooth curves. Rational functions can have some hiccups, some missing things. So if your denominator equals 0, if the denominator of a rational function equals 0, we do get a domain problem, a discontinuity, at that value of x, the x that makes that denominator 0. It has very little to do with the numerator. So what do you use the numerator for? Really, x-intercepts. The numerator will give you x-intercepts, and it will also tell you whether your denominator is a hole or a vertical asymptote. So we'll be comparing that. Now, these things, these domain issues, these values of x, they will also cause graph issues. We're going to jump right into what those are. So if your denominator equals 0 at this x, then at x, there's going to be one of two types of discontinuities. The first is a hole, or what's called a removable discontinuity. Now, why they call it removable is that if you define your function with just one additional point, you can put that point in there and you can fix the discontinuity. That's what's called a removable discontinuity. As you get into calculus, you might hear that. It means nothing more than a hole in your graph. So don't let this phrase really confuse you. You can call it a hole and everybody's going to understand what you're talking about. The removable part of it is you can fill the hole with 1 point. That's it. So what happens when the factor, and so here's when you get these. You'll get a hole when the factor that is causing your denominator to equal 0 can be canceled. Now, what would it be canceled with? Well, it would be canceled with something on the numerator. And you heard me say about a minute ago that the numerator will tell you whether your domain problem is a whole or a vertical asymptote. So here's the whole rundown of what we do with these. First thing we do is we look at our fraction function, our rational function, and we factor the whole thing. Then what we do is we look at our denominator. We take those factors that we have, and we set them equal to 0, and we discover that, hey, all those factors that are equal to 0 are going to cause some domain issues for us. The ones that you can cancel stand for wholes. The ones that you can't stand for vertical asymptotes. Now, here's the deal. You can't just cancel them and say, I don't have a hole anymore. I fixed it. You can never fix domain problems. Oh man, it sounds horrible. It's kind of like baggage in relationships. It never goes away. It's always hidden. It's always right there, right? And sometimes it pops back up. You can't get rid of that stuff. Like, it follows you. And so that's kind of what a hole does. It's going to look like it's gone. You're going to cancel it, but all that's telling you is that what you just canceled out is a hole in your function. It's going to go along like this. You're going to go along. You're going to be missing a point. And then it's going to continue. That's what a hole or a removable discontinuity looks like. Is it continuous? No, it's not. You go like this and you go, oh, I can't continue on without lifting my pencil off the paper. You're not allowed to do this and go around. That circle's there to say you're missing a point. So you're going, you jump, you miss a point. That's called a hole. One thing about this, what's very interesting is that in calculus, we talk about limits. And the limit would actually exist here from left and right. It goes to the same value. The value itself is not there, which is why it's a discontinuity. It's not continuous, but the limit actually does exist when you get there. Interesting. So we're going to use, and actually these are really useful because we're going to use these as a type of point. I know the point's not there, but it is something that your graph has to interact with. So if we can find the location of a hole, we know the graph has to sort of touch it, not complete it, and leave it. So we're going to use that. We're going to use it kind of like a point. So the whole rundown about holes is we factor and you look at your factors on the denominator. If you have more than one, if you have one, fine, that's whatever that is. We look at them. And if you can cancel them, then that domain problem is going to be a hole. So we factor, we find our domain problems, and then we define them. I'm going to show you how to do that after I talk about a vertical asymptote and what that means. So if we can cancel it, then what you just defined is a hole, and we can find the value of that hole and find out where that is. So what happens if you can't cancel that factor? Well, a vertical asymptote happens when the factor that's causing your denominator equal to 0, it can't be canceled. And here's what they look like. They kind of, man, I like Star Wars, so kind of reminds me of force field or like, I don't know, Star Trek or whatever. It's like this thing where I always used to picture it. Now I'm gonna really maybe date myself here, but like Star Wars Episode 6, when they're going to the Death Star, if you haven't watched it, spoiler alert here, and there's always one dude that doesn't pull up in time. Like they hit the force field, they hit the force field. Every movie that has force fields, it happens. Well, this is kind of like a force field. So this graph is going to have to pull up before it hits it or go down before it hits it. And it cannot cross it. Why? Because at that value, your denominator would equal 0. We know that that is not okay. So if your denominator equals 0 here, you're just frankly missing a point. If your denominator equals 0 here and you cannot cancel out that factor, then what you end up getting is you end up getting this going to infinity sort of idea. And that has to do with when you're dividing a number that's very close to 0, you either get positive or negative infinity. For instance, take like 100 and divide it by 1. You're going to get 100. Take 100 and divide it by 0.1. You're going to get 1,000. 0.01. You're going to get 10,000. Take 100 and divide by 0.0000001, and you're going to get something that's really, 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 really big or really, 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 really negative, depending on whether you're divided by a positive or negative number. And so that's kind of what's happening. If this value equals 0 on your graph, then something just to the left of it and just to the right of it is either going to cause something really close to positive infinity or really close to negative infinity. And for that reason, I'd kind of just described limits to you. Here's what happens. You're going to get one of 4 looks. Your graph is going to look like this, or this, like this, or like that. Those are the 4 cases that you're ever going to get with a vertical asymptote. And you can have several on one graph. Here's the main points. A whole happens when you have a factor that causes your denominator equal to be 0, and you can cancel it out. Vertical asymptote happens when the denominator has a factor in it that creates it. Let me repeat that. Happens when there's a factor on the denominator that causes your denominator equals 0 and you can't cancel it. You're going to have one of 4 cases here. You can have all of these things in one graph. What we're going to be doing here is when we start identifying those factors that cause your denominator to be equal to 0, we're going to identify whole or vertical asymptote. You're going to have one of 4 cases. Where these 4 cases happen, this is kind of interesting. Man, I hope you remember about multiplicity. If the multiplicity of the factor that's causing your denominator to equal 0 is even, you're going to get one of these 2 looks. If it's odd, you're going to get one of these 2 looks. So odd multiplicity had a lot to do with whether we're crossing the x-axis or even had to do with whether we're bouncing. For vertical asymptote, a vertical asymptote or vertical asymptotes, the multiplicity of the factor that's causing your denominator to be equal to 0 is going to tell you whether you're doing this odd, opposite, or even symmetrical sort of a multiplicity. You're going to either opposite infinities or the same infinity. So these 2 are going to happen when you have odd multiplicity for your denominator factors. Odd multiplicity. When you have the same sort of symmetry, that comes from evenness. And this is going to come when you have even multiplicity for your denominator factors. That's about it. What we're going to do right now is I'm going to give you some examples because this is not vague. I've explained it well on what these things are, but it's still sort of out there. We haven't made it concrete yet in terms of examples. So the long story, hopefully made short, is you are going to be looking at your denominator, you're going to factor it. You're going to set it equal to 0, and you're going to identify that you have one or several domain issues. Then what you're going to do, you're going to look at the factors that are giving you your domain problems. You're going to look to see if that particular factor can be canceled. If it can be canceled, then the domain problem you just identified is a whole. You cancel the factor out, you plug in the value, you find the whole. And it gives you kind of a type of point you're going to use the graph. If you look at the factor and you cannot cancel it, then what you've just identified is called a vertical asymptote. We put a little dotted line, acts like a force field. We absolutely do use our graph to interact with this. It's a very strong graphing tool, but your graph cannot touch it. It causes discontinuities. In either case, it's just a different type of discontinuity. You can have one of 4 types of vertical asymptotes. With odd multiplicity, you're either doing this or you're doing this. With even, you're this or you're doing this. And it kind of depends on the sign around it. So we're going to be looking at that as we get into sketching. I can't tell you right now, oh, you're always going to get this one with odd. That's not true. It really depends on how your signs are interacting around that vertical asymptote. The reason why this one goes to infinity and infinity and these 2 infinities is because when you divide by 0, it's undefined. You cannot plug in a point and do that. But something just to the left and to the right of 0 is dividing some number by a number that's very, 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 very small. Dividing any number by a number that's very, 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 very small is going to give you a very large number, either positive or negative. That's why we get these infinities. So let's take a look at some examples and get a feel for wholes and vertical asymptotes a little bit more clearly. All right, so we're ready to identify whether or not we're going to have some domain issues and what those domain issues are. One thing I want to caution you on is just because you have a rational function, these are all rational functions. We have a polynomial over a polynomial and a fraction. So that means variables on both the numerator and the denominator. Just because you have that doesn't mean that you have to have domain issues. It just means that if you do have domain issues where your denominator equals 0, and that's the only type of domain issues that we are going to have in rational functions, there's no square roots here, no logarithms, nothing like that. If you're going to have them, we can define them. Furthermore, if you know how to define them, you can use them to graph. So it's kind of nice to have these things and understand what they are because we use them to graph very easily. So let's take a look at the first example. If you heard what I said in the first part of the video, we're basically just going to factor everything, both the numerator and the denominator. We're going to do that first. So when we look at f of x, we have x plus 3 over x minus 4. That's already totally factored. So when I teach you to sketch, what I'm going to be doing is telling you we're going to find x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, oblique asymptote if there is one. There's either horizontal or oblique. And then we're going to find a few points, and we're going to be using that to sketch or graph these rational functions. Right now, we're just on like the first step. So we're going to factor, we're going to look at our denominator first, and you're going to say, hey, let's set that equal to 0 and see what we get out of it. So what we do first, we factor everything, we say, okay, we're done. Let's set the denominator equal to 0. And you're going to solve that. So we're sort of using the zero product property after we factored. It's already factored. So it becomes its own factor. We set that equal to 0 and then go, okay, let's solve. That would be x equals 4. Then what we do is we added 4 to both sides. Then what we do is we look at the factor from where we got that discontinuity. This right here says one thing about this function. This says if you allow x to equal 4, you're going to have a serious problem. You're going to have 7 over 0. Wait a minute, can you have 0 on the bottom of your fraction? You go, no, you can't. Why? It's undefined. Like, there's no way to get that. It'd be saying you're taking 7 real pieces out of something that doesn't exist. It's impossible for us to define that scenario. We cannot do it. So that is something that's undefined. That's a domain problem. So we know on our domain that we would say, all right, domain would be all real numbers except that x can't equal 4. If it does equal 4, we have a big problem. So, from what we know though, we're going to look back at that factor and determine whether we can cancel that or not. Because what that's going to do is say, okay, yeah, you can't, kind of weird statement, but yeah, you can't allow x to equal 4. So at x equals 4, what do you have? One of these two things where you can't allow x to equal 4. You either have a hole or you have a vertical asymptote. In what way can't you let x equal 4? Where you're simply missing a point, or whether you have sort of a force field, like a vertical asymptote. This is where we look back at our factors. We go, all right, look at x minus 4 and look at x plus 3. Can you cancel the x minus 4? If you see another factor of x minus 4 in the numerator, the answer is yes, and this would become a whole. Well, we don't see that. We look at x minus 4 and go, well, the only other factor is x plus 3. Can I cancel x minus 4 with x plus 3? No, I can't. And that right there defines what this is. So again, we factor everything, got it. We look at our denominator and set those factors equal to 0, and we solve them first. No matter what, you do not cancel first. We solve them first. This gives us our domain. It says, hey, I can't have these values. Okay, how can't you have them? Well, I can't have them because I can't cancel this. That means this is a vertical asymptote. So at x equals 4, we have a vertical asymptote. More than that, we're going to look at the multiplicity of the factor that gives us that vertical asymptote. Holes don't really have a multiplicity. You don't really care that much about them. But for vertical asymptote, or vertical asymptotes, we do. So we look back and go, okay, that had a multiplicity of 1. That's odd. I don't really care about the value of that power. I care that it is odd. Here's what that means. At x equals 4, we are going to have either this or that. In this one case, just because we have a positive out front, there's nothing fancy going on, we're going to have this case. It is certainly going to look like this. That's what's going to happen around that x equals 4. We have an odd multiplicity vertical asymptote. Going to look like one of those, specifically this one. In general, you can't tell unless it's sort of a simple rational function. If there was a negative up front, we would switch that around. So it looks like that, and that's pretty much the whole thing. So we're going to move on. We're going to do a few more of these to get the real feel for how vertical asymptotes interact with our graph, and then we'll be good to go. So let's look at the next one. We're looking at g of x. We get -2 over x minus 1 to the second power. We're going to go through the same process. So we're going to look at this and go, all right, we're going to factor both the numerator and the denominator. Well, the numerator is factored and the denominator is factored. I've kind of made these easy because we know how to factor. We're not going to spend a whole lot of time doing that. So we look at that and go, okay, that's factored. The next thing we do is we take our denominator and we set the factors equal to 0. I don't need you to set x minus 1 squared equal to 0. I need you to treat this sort of like we treated x-intercepts and go, all right, what's the real factor? The real factor is x minus 1. You just happen to have it twice, which is where we get multiplicity. It's a repeated asymptote in this case. So we're going to set x minus 1 equal to 0, and we're going to solve it. So we get x equals 1. Now here's what that means. So we take a look and I go, okay, what was the purpose in us setting our denominator equal to 0, or the factors of the denominator equal to 0? We're basically saying that's a problem. That's a real problem, because if you know this, you know that if your denominator equals 0, we have some domain issues. We just never defined those before. You've known this since intermediate algebra when you did rational functions. Usually it's like chapter 7 in that class. So you do this, you go, all right, that's a problem. I just know that domain-wise, I can't have 1. Now we're saying how we can't have it. I know that's a weird statement, but it's going to fall into one of two categories, either a whole or a vertical asymptote. So we look back at this and we go, right, I know that x cannot equal 1. So at x equals 1, we have one of two discontinuities. That actually needs to make sense to you. If you can't let x equals 1, which is true, you cannot have that, then at x equals 1, we have a problem. You're defining the problem. Do you see how we make a little switch there? You can't let x equals 1 for the function, and so we have one of two problems at x equals 1. So then we're going to look and see what we have. So we look back at our factor here, and we look at our numerator, and we see whether we can cancel this factor with anything on the numerator. And you go, yeah, no, there's no factor up there besides 2, or you can consider it -2, but there's nothing that will allow us to cancel the x minus 1. So you simply say, no, I can't cancel it. If we cannot cancel the factor, then we do not have a whole. We have a vertical asymptote. So we're going to write that. So we have a vertical asymptote, something like a force field, where your graph cannot touch it. Certainly interacts with it, but it cannot touch it. Now we're going to define that a little further. Look back at the factor from where we got that vertical asymptote. We go, okay, this came from the factor of x minus 1. That has a multiplicity of 2. That's an even vertical asymptote. Even multiplicity, even vertical asymptote. So what that says to us is that this vertical asymptote is going to look like this or like this when we graph it. It's either going to do that. Due to the nature of even is typically symmetrical about the y even functions are. So this is sort of symmetrical about a type of y. A vertical asymptote is a type of y. It's just sort of shifted over. Wait a minute. Do you remember that adding or subtracting inside of a function is a left shift or a right shift? That's actually a shift of the y equals 1 over x squared graph shifted to the left one spot and reflected. Wait, what? That's a vertical asymptote. It looks just like this. That's what that is. And in the next video, we're going to graph some of those with transformations. It's going to make this stuff really gel together. You just need to understand a vertical asymptote before we actually get there, which is why we're doing this. So this is a vertical asymptote. It's going to be even, so we're going to have this going to the same sort of infinity, either positive or negative. I know, because I've done the transformations already, that negative makes it go downward. So it's going to look just like this around that x equals 1. We're going to have the vertical asymptote. So you might have a question right now. What do the numerators have to do with anything? Well, the numerators will let you know two things. Number one, if you can cancel that factor, it's going to let you know that you had a hole. If you can't, it's going to let you know you had a vertical asymptote for that particular x value for which you got a domain problem, and you look at the exponent of your factor from where you got that. It also tells you your x-intercepts. So it is valuable. It's just not going to give you any specifics for a vertical asymptote, other than it is one or it's a hole. So here, your x-intercept would be -3. You set your numerator equal to 0 for those. Here, you don't have an x-intercept, so -2 can't equal 0. So this would say you're not crossing the x-axis ever. How could that look? Is it possible to have this vertical asymptote without touching the x-axis? The answer is, what this graph really looks like is about like that. Now I haven't found the y-intercept. That's going to be -2. I haven't found that, but that's about what that graph looks like. We're going to study that next time. Okay, let's move on a little bit. So we're looking at h of x. We're saying, hey, 2x over x squared minus 4. The first thing that we're going to do in graphing or finding any sort of discontinuity is we're going to factor everything. So we look at our numerator and go, okay, that's factored. Look at our denominator and go, all right, I can factor that as x minus 2 and x plus 2 due to the fact that it's a difference of squares. Then what we do is we define our domain. You don't start looking to cancel right now, you're defining right now. So we look at all of our factors on our denominator that have variables. So we see x minus 2 and we see x plus 2. We're going to set both of those equal to 0. Sort of by the zero product property, if you set your whole denominator equal to 0, then you could set each factor equal to 0, right? That's the zero product property. We're just sort of shortcutting that. We're going, all right, I'm going to set all of my factors equal to 0 because if any of these factors that have a variable are equal to 0 on my denominator, it makes the whole denominator equal to 0. That's why we factor first, because it lets us identify this stuff. And we're going to keep going and say, all right, I'm going to add 2, I'm going to subtract 2. And these are my two domain issues. These are values that I cannot plug into my function right now. If I do, I get something divided by 0. I get a real number, either 4 or -4, divided by 0 in either of these two cases. Try it for yourself if you want to. That means that we have domain problems. This is an issue. So our domain says we cannot let those happen. If you want to write your domain, that's pretty much it. There's other ways to write that, but that's pretty much it. So you go, yeah, I can't let that happen. And by the way, we've studied interval notation for domain. We've studied set builder notation for domain. So we've done that before. This is just saying you can't let these things happen. Keep that in mind. Please understand this. When you find your domain problems like this, these are values that you're not allowing. This and this just defines how you're not allowing it. Are you not allowing it by making it a whole? That's if you could cancel them, or 1. Or are you defining it by making it a vertical asymptote? That's if you can. You get a force field out of it. So we're defining now what these domain problems are going to create graphically. I hope you see that. I hope you see that these values can't happen. Now we're defining graphically what that looks like. So we look back at the factors that gave us these domain issues. We look back at x minus 2 and go, oh, that had a multiplicity of 1. What that means is that this factor with the multiplicity 1 gave us this discontinuity, said x can't equal 2. So we're going to define how that looks at x equals 2 graphically. So at x equals 2, what type of discontinuity do you have? What type of I can't equal this do you have? Well, because it has, you cannot cancel that factor. So I can't cancel x minus 2. I'd look at the numerator, can't cancel it. So at x equals 2, and because of our odd multiplicity, I have a vertical asymptote with odd multiplicity. So I know right now that at x equals 2, we sort of get this sort of force field where we're going to be interacting with it in one of these two ways. The same exact thing is going to happen here. So we look at that and say, yeah, I can't allow x to equal -2. How can't you allow it? With a whole or vertical asymptote? Let me take a look at my factor. At x equals -2, I got that from x plus 2. That factor cannot be canceled. There's no x plus 2 factor on the numerator. It also has a multiplicity 1, so this is also a vertical asymptote with odd multiplicity. And we're going to do that every single time. You get a lot of vertical asymptotes with odd multiplicity. Just saying, that's very, very, very common. If you want to look at your numerator, you should right now start kind of be thinking, do I have any x-intercepts there? And you do, actually. 2x would equal 0. X equals 0 is an x-intercept. So your y-intercept is 0 and your x-intercept is also 0 here. So that's kind of neat. Now the next thing that we're going to do is we're going to do this one. It's the last one we have. We're going to see both a whole and a vertical asymptote. Let's show you where we get the whole idea from and how to define that missing point. All right, so let's go for it. The first thing we do whenever we get a rational function and we're trying to graph it, or we're trying to find the asymptotes, or we're trying to find the x-intercepts, we basically factor everything. We define our denominator, our domain first, always first, and then we start defining what that domain means graphically. After that, we do x-intercepts. And the reason why we don't go the other way is because occasionally, like here, you'd start defining x-intercepts first, and then you'd cross them out and go, well, what happened? Did I cross that x-intercept? No, that was actually a whole, you just didn't realize it because we did it backwards. So we factor everything first. On the numerator, that means x minus 3 and x plus 3. On the denominator, that means x plus 7 and x minus 3. That's x squared plus 4x minus 21. So here's what to do and what not to do. What not to do first. Don't run off and say, oh, I have x-intercepts at 3 and negative 3. No, you don't. Here's also what not to do. I'm just going to cancel this to make it easier. Don't do that. Define your denominator first. This is your baggage. Even though you can cancel these, and you will, just be patient. Even though you can cancel those, that baggage stays with this function. This says you can't plug in 3. You ain't never going to be able to plug in 3. Ever. Like, you could define the function differently and allow 1 point, but you cannot let that 3 happen ever in the function the way that it's written. So trust me, we're going to factor first, and then we're going to define the domain. How we do that is to look at the factor denominator and set each of those factors equal to 0 pretty much by the zero product property. So x plus 7 equals 0, and x minus 3 equals 0. And that's going to give us two problems, or two discontinuities on this graph. So if we subtract 7, we get x equals negative 7. If we add 3, we get x equals 3. Now keep in mind what that means. These are values that are not allowed in this function. If you allow x to equal negative 7, you're going to have a value over 0. If you allow x to equal 3, you're going to have 0 over 0. 0 over 0. Isn't that 1? No, it's not 1. It's a problem. It's a problem anytime your denominator equals 0. So these guys right here, they're kind of bad guys. Like these are things, as far as our function is concerned, it can't handle. So we have just found our domain. X cannot equal negative 7, and x cannot equal positive 3. Those are not okay. Those are discontinuities in both cases. Do this first. Let your denominator define your domain for you first. Then we start defining what these discontinuities look like. You go, okay, I know I can't allow x to equal negative 7, and I know I can't allow x to equal 3, but what's that mean for us? Like, how does that look? This is where we go back and we go, okay, let's take a look at the x equals negative, or can't equal negative 7 first. That came from a factor of x plus 7. So we're going to look at that factor. Can you cancel out that factor with the numerator? No, I don't see any x plus 7 factors up there. So what that's telling us is that because I cannot cancel out this factor, that's going to create this thing where I get a number over 0, and anything that's really close to that 0. So like if I plugged in 7.00000001, I'd get a number over something very, very, very small. That's going to give me either a positive or a negative infinity depending on my signs. If I plugged in negative 6.9999999, so negative 7.00001 or negative 6.99999, in either case, I'm going to get like number divided by something super close to 0. Well, what that's going to do is that's going to give me something that's going to positive or negative infinity. That's why this thing is a vertical asymptote. So this cannot be canceled. It says you're going to get something that's that you can divide by really close to 0, giving you a infinity sort of concept. So all that to say, at x equals -7, we have a vertical asymptote. And because the factor has a power 1, it's an odd multiplicity. Vertical asymptote looks like this or like that. So that's what we're going to get graphically. Then we continue. Okay, we also know that x equals 3 is a problem. We already defined our domain. You do this first every single time. You define your domain first for rational functions. Then we go, all right, because I can't have that, in what way can't I have it? Do I have a whole or a vertical asymptote? I'm going to look back at my factor. X equals 3 or x can't equal 3 came from x minus 3. That factor's right here. So I look back at my function and go, oh, look at that. I can cancel that factor. What that does is that says at x equals 3, you are going to have a whole. Now here's what to do with that whole. A lot of textbooks and teachers I've seen just say, oh, you have a hole there, great. But it's very confusing as to what that hole does. Is that hole in the x-axis? Is the hole, like, where is that hole? You need to find where the hole is. You need to find that missing point. Don't miss that point. Like, you need to do the next step. Here's what to do, and do it in this order. Factor, define your domain, define what those domain issues are like we've just done. For a vertical asymptote, you're defining what type you have, either odd or even. This or this, or the reflected version of those, depending on the multiplicity of your factor. When you get to a whole, cross it out, and this will allow you to redefine your function. You see, the reason why we don't do this first is because a lot of times if you let students cross these out first, they miss the fact they have a whole. But the fact that this does simplify leaves you with a simpler function. Now, this is quite interesting, and this is where students come up with a very common misconception, like, oh, well, can't I plug in 3 here now? Like, that doesn't have a domain problem anymore. Yeah, exactly, that's what it looks like. That's why you define your domain first, because here, it certainly does look like you can plug in 3. And in fact, we're going to, but here's what we're going to do with it. This says you can't plug in 3. You already know that. You defined it. Don't change this. This never changes. You can't ever make the domain better. You only make it worse. So this does not get fixed. You can never plug in 3. But if we allow ourselves to plug in 3 here, listen carefully, this will show us exactly where that hole is on our graph. The thing that our function must intersect with. So it's basically finding a point. So if I plug in 3, so allow this to plug in the thing that you can't plug in, we would get 3 plus 3 is 6 over 10. 3 plus 3 is 6 over 3 plus 7 is 10. If we simplify that, we get what? 3/5. So divide by 2, we get 3/5. Here's what that means for us. There will be a hole at exactly the point 3, 3/5. Now we'd use that. We'd say, all right, I'm going to go to the value, or graphical value if you want, the point 3, 3/5. So over 1, 2, 3, up like just a little bit. And I'd put a hole there. I'd say at that value right here, you're going to have a hole. So your graph looks something like this. It's going to come to that missing point, and then it's going to continue. It's kind of an awkward looking graph, but it's very valuable. Here's the last thing I'm going to say to you, and then we're going to end. This graph will look exactly like this graph. And it's hard for students to understand. This canceling out, it does make this graph look like this graph. The only exception between these two is that this will have a missing point right there. So this graph looks like this one. This graph itself would not have the missing point. But because it came from this one, we defined our missing point. We said, okay, now what to do with this hole? Plug it in, get the value of where that hole is. It's right there. And this graph is going to look just like that one. We'd graph in the same exact way. Hey, does that still have a vertical asymptote at x equals -7? Yes, it's still odd. Yes. Does it still have an x-intercept at 3? Or -3? Yes, just like that one. This does not have an x-intercept at +3. That was canceled out. So these graphs will look identical beside the fact that it has a missing point or a hole. So I hope that makes sense. I hope that you have an idea of when you get vertical asymptotes and when you get holes. That's about all I want to do right now. We'll continue with different types of asymptotes and talk about graphing a little bit later. Have a great day.